Hello out there, welcome to a video about transformer theory, more specifically transformer action. It's going to be a series of 3 videos. This is the first video. In this video, we're going to talk about self-induction and how counter EMF is produced. The next video will be an energized transformer that's not loaded and all the transformer action that happens and the steps that happen within the transformer. And then the third video will be a transformer under load. So let's get started. I'm going to share my screen. And as you guys can see on your screen, I have a drawing of a coil around a core. And then at the top here, I just have the title of self-induction and how that basically creates this counter EMF. And beside that, that's XL in brackets. I'm not going to talk about inductor reactance. That is a part of the process, but that's more into the theory instead of transformer theory. Okay, let's look at what we got here. So I have this wire. It's wrapped around the back of this core, goes around the front and then back and front. And then you can see I got a few wraps and then it comes back. So assume that this wire is connected into a source of some kind. Therefore, current is going to flow. And I'm just going to pick a direction, so I'm saying up. So that means the current's going to come in through this wire around the back of the core, over the top, the front, around the back, down the front, up the back, down the front, and so on. So that's how current's going to flow. Now this little dotted line here is just to help us visualize that if I took a hacksaw and then cut down the center of the core like that. Now I couldn't actually do this in real life because if I did, current wouldn't flow and I would ruin my coil. But as a visual technique to help us show you what I'm drawing here. So what I'm going to do is I'm drawing the core, now the side of the core, basically this part right here. And then there's going to be wires coming over the top, but I'm just going to draw the cut version, the cross-sectional area, the wires on the top, and then there's going to be wires on the bottom. Now let's use the current flow that I had in the original drawing here. So I said the current's coming up around the back and then up the front. It'd be, if we're looking at it, it'd be towards us and then it'll go down and then away from us. And then at the top it'd be towards us and down it'd be away from us. So if I went on the right hand side here, following the arrow, pretend that there's a wire here coming around the back, that current is going to go towards us, which we draw as a dot. And then if that wire is to continue on, the front, the current would go down and then it would go away from us and then up the back towards us and then away from us and then towards us and so on. So hopefully that makes sense what I'm doing here. This is just a cross-sectional area of this, or a cut I should say, of what's going on the left-hand side. Now what I want to do is I just want to focus on, let's say, these two guys here, and I'm just going to make them a little bit bigger. And I'm going to draw the X's. Again, you guys should know this from theory class, that the X's mean current going into the page. Okay, so the current's flowing. And we know that magnetic fields are tied to current. So the larger the current, the larger the magnetic field. But we also know the direction of the magnetic field with our left-hand conductor rule. So the thumb is for the current direction and the fingers are for the direction of the magnetic field. So if I was to do that on the page here, I would figure out that the current would spin counterclockwise. Now, the other thing that we want to talk about is the sine wave. So let's just draw a little sine wave on the right-hand side here. And I want to focus basically from 0 degrees to 90. So this little area right in here as the current is growing. Well, we know as the current grows, the magnetic field grows too. So we can represent that by one little, half circle here of magnetic field, but let's just draw another one as it's growing, another one as it's growing, and one more. And then let's just kind of do the other side if there are 2, however that works. Okay, I got 3 coming out, 4 going in. Let's even that out. Okay, so we're showing that this magnetic field is actually growing by the amount of lines of flux. So now we have a magnetic field, we have a conductor, and we have some virtual movement. So there's a relay, relationship here between this conductor and the magnetic field, there is relative motion. So there isn't any physical motion, but because of this expanding magnetic field, and it's expanding around this conductor, around the other conductor beside it. Now this would happen all along the chain, but again, I just want to focus on one little area. With this relative motion of a magnetic field and a conductor, we can now use the left-hand generation rule. So let's see what's going on. Well, first of all, we know that magnetic fields travel from north to south. So if I had a north pole here and a south pole here, that's basically what's going on with the arrows going in the upward direction here. So there's our north to south. If you remember your left-hand generation rule, it's the first finger. And let's draw it, I don't know, over here. So I'm going to draw a little first finger here going up along with my north and south pole, because the first finger is for a field. Now, the thumb is for thrust. This is going to be a virtual thrust. So again, the conductor doesn't actually move or actually thrust from right to left, but let's wrap our head around this, what's going on, this relative motion. If we had a magnetic field going from basically left to right here, because it's expanding, that is the same thing as a conductor physically moving from right to left. And that's the arrow that we need to make our left-hand generation hand work. So now I have my thumb going from right to left. So I'm going to draw it over here on my little handy-dandy drawing. Let's just try that a little bit here. So it's basically, I got a really long finger going on here. Okay, well, this drawing isn't going to be exact, but also the thing with my drawing is, because I'm a little boxed down in the corner here, is this is the palm part facing you. So there's my palm, my hand. The other fingers are curled in like this. And then it's the center finger that's going to be pointing, there's the fingernail there, pointing right at us. Because that's how it works. We have a thrust going from right to left, a magnetic field going up. Now we have a current that's going out of the page. Well, the original current was going into the page, but now we just induced a current going out of the page or coming up towards us. What's going to happen is now we have the original current, again, going one direction. We have this counter EMF that creates a counter current. Now, for whatever reason, we don't say counter current, but it's there. We just say a counter EMF. So the counter EMF is, again, this magnetic field is creating this counter EMF. And then because it is a closed circuit, then we have self-induction. And we have this current going in the opposite direction, and then we're going to have a resultant current that's going to be a lot less than the original current, and that's basically what's happening. That's our counter EMF. Now, I don't want to complicate things with this whole transformer theory, but we're basically done for transformer action and self-induction and how it creates this counter EMF, which then results into a low current flowing. So this current here that's flowing, and I should probably change the color because I don't, the red current is going in the opposite direction. So let's just go back to black, make this, again, darker. That's what I'm talking about. That's the original current. It's just going to be smaller because of this counter current coming. If you were to actually do this with the magnetic field now collapsing, so from 90 degrees to 180 degrees, you'll see that they go in the same direction, and then that adds to why current lags. But again, that's a whole other theory thing. In this these video series, I just want to talk about the counter EMF. I'll see you in the next video.